Welcome to the webinar today. My name is Matt Cederberg. I'm a co-founder and chief strategy officer at Coreform, and I'm excited to introduce Bill Ellis, HPC computational engineer at the United Kingdom Atomic Energy Authority. Today's webinar is called Eating an Elephant, How I Efficiently Meshed a 4,000 part assembly using Coreform Cubit. First, I'll introduce Coreform, and then we'll introduce the United Kingdom Atomic Energy Authority. Then Bill will get into the meat of the webinar and explaining how he ate this metaphorical element by meshing this very large massed U model with Coreform Cubit. It will include a live demo and also some of his strategies and tips and tricks that he developed to accomplish this task. He'll share the simulation results, and then we'll conclude the webinar. Coreform is developing next generation finite element analysis applications. And so we have two pieces of software: Coreform Cubit, which has been around for decades and is best in class for meshing, and also Coreform Flex, which is our next generation isogeometric analysis solver. And so whether you're looking to radically improve your simulation process by running accurate FEA simulations directly in fully featured CAD, which we can help you with Coreform Flex, or just get better results with your existing solvers, which we can help you with Coreform Cubit. We're just eager to help improve your simulation efficiencies here at Coreform. We'll go into a little bit more with Coreform Cubit to introduce that software now. That's the focus of this webinar. Some of the reasons that Coreform Cubit is used are for its ability to import CAD. We can import CAD natively from a variety of different file formats. We also have a lot of tools to help clean up dirty CAD. The semi-automated hex meshing is one of Coreform Cubit's kind of unique strengths. We do hex meshing very well. There's a lot of different ways to decompose the geometry and create high quality hex meshes with maximum control of mesh properties. A lot of people use Cubit because of the Python and scripting available, and also the flexible licensing that we offer. And with that, let me just do one more introduction of Bill. So again, Bill is a HPC computational engineer in the Advanced Engineering and Simulation Group at the United Kingdom Atomic Energy Authority, led by Andrew Davis. And prior to this significant project that he's about to introduce to you, he'd only been using Cubit a handful of times prior to starting this project in May of 2023. And with that, let me turn the time over to Bill.
Thank you very much, Matt. Hello, everyone. So I'm Bill. I'm from UKAEA, or the United Kingdom Atomic Energy Authority, which is a public body interested in fusion research and development in the UK. And UKAEA is comprised of several key facilities, including the Culham Centre for Fusion Energy in Oxfordshire, which is where I work, which until very recently was home to the world's most powerful operational fusion device, the Joint European Torus, or JET. I say until very recently because sadly decommissioning on JET started recently, so I can't quite say it anymore, but that was very true until recently. You might have seen in the news a couple of years ago, in December of 2021, scientists and engineers at UKAEA managed to achieve 59 megajoules of sustained energy output using JET, which is a great achievement and makes a good case for kind of future fusion research endeavors. And UKAEA's mission is really to lead the commercial development of fusion power and to position UK as a leader in sustainable nuclear energy. So that's the goal. So yeah, more specifically, I work within the Advanced Engineering and Simulation Group, which is led by Dr. Andrew Davis. We're a group within the UKAEA Computing Division, and we look to provide simulation solutions to deal with a wide range of physical phenomena relevant to fusion reactors. So electromagnetics, fluids, heat transfer, particle transport, all the good stuff. And we look to really exploit the HPC resource we have at our disposal to push the fidelity of these simulations. And to make the most out of this HPC resource, we have to utilize scalable software tools. So we use a lot of Moose for FEA and CFD, which is the multi-physics object-oriented simulation environment. We use OpenMC and DagMC for neutronics, and we feed our software stack with models and meshes prepared in Coreform Cubit. So a couple of years ago, in 2023, seems like yesterday, Sergey and Luca in the material simulation group, which is also within the computing division at UKAEA, were interested in modeling various physical phenomena on a full-scale tokamak model. The only problem at the time being that we didn't have a simulation-ready full-scale tokamak model. And I had been in the group for a year or two at this point, and I was given the task of doing the geometry prep for this model and getting it up to scratch. So, how do you start preparing a tokamak model? Firstly, you have to decide which tokamak you're looking to model. And fortunately, you've got a fairly limited set to choose from, so that makes your decision somewhat easier. We decided to look at MassDue, or the Mega Ampere Spherical Tokamak upgrade, as our reference tokamak geometry. It's one of the reactors we have on site at Cullen. And so, yeah, fortunately for me, I didn't have to start from zero. I got sent a model by Andy that was previously used for neutronics analysis and looks a little bit like this. This is great for me because I don't have to start from scratch. It's already got plenty of detail. However, it is missing some structural support that's going to be necessary for the simulations we want to run. So the first step I have to take is to go onto our document management system, find the CAD and the drawings of the components that are missing, and I need to implement them into this model. And I have to thank Johannes and Andrew for their help here because they know Mast inside out and they know how a lot of the pieces actually fit together. So they were really helpful here. And once I had implemented these missing components, the model ended up looking something like this, which is structurally sound, hopefully. And it's got a couple more magnets in it. And actually, at this point, we're ready to take our CAD assembly and we can import it into Coreform Cubit, where it will look a bit more like this. So, how do you eat your elephant? What's the big picture? What are the main steps you need to take to get from importing a CAD model into Cubit and actually having a mesh that you can use in Moose or whatever simulation framework you'd like to use? The first thing you're probably going to have to do is clean up your geometry, which can refer to a variety of practices. This could refer to healing operations within Cubit, which kind of help circumvent problems that occur when you go between CAD kernels of different numerical precision. So healing can kind of help automatically alleviate some of those issues. Cleaning up geometry can also refer to removing obvious large overlaps between components. And it could also refer to removing extraneous detail. So you may have a component that has wires and bolt holes that are not necessary for your simulation. And actually removing these will help you reduce your element count and will make life a little bit easier. So you've got to clean up your geometry first. Then you have to imprint and merge. Imprinting and merging is a practice that refers to forcing components that are next to each other to have like topology. And once they have like topology, and that's the imprinting bit, you kind of imprint the shadow of one component onto another, onto an adjacent one. Once they have like topology, you can merge the like pieces together. So you can merge similar surfaces or curves or nodes. This way, your resulting mesh will be continuous across component boundaries, and therefore in your simulation, your field results for whatever you're simulating, say it's displacement, will be continuous across that component as well. This is somewhat easier said than done with very large geometry or very large CAD assemblies. Once you've imprinted and merged, then you can start declaring blocks and side set definitions, which help you declare material properties and boundary conditions within your simulation. And then you can generate your mesh, and then you're ready to run whatever simulations you'd like. And after talking a little bit more, going into a bit more detail about these, we'll look at some useful commands and some other resources I found really helpful in this project. So we're going to get straight into imprinting and merging, because that's the crux of this project, really. How do you effectively imprint and merge CAD assemblies with many, 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 many components? And this kind of, was where we got the title of this webinar from. It is eating an elephant. You've got this monumental task. How do you break it down? You break it down by doing things in small bites. If you have thousands of components in a CAD assembly, you can't imprint volume 1 with volume 2, and then volume 2 with volume 3, and then volume 1 with volume 3. It doesn't make any sense to do it that way. One, it makes troubleshooting really hard because your search space for any problems you run into is massive, and it's time consuming. It's difficult. So what you want to do instead is do it in bites. You want to group components together, and I've got a picture on the right of one of the groups that I had in this CAD assembly, and imprint and merge based on groups. And that will reduce your search space for troubleshooting. You'll have a problem with group 2 instead of volume 3607, which is a lot easier to narrow down problems this way. The other key thing I'd say you want to use is tolerant imprinting. When you have large CAD assemblies with many components, you are inevitably going to run into really small but still existing overlaps. And normal imprinting can't always handle geometry which has slight overlaps. Tolerant imprinting, as the name suggests, allows you to imprint within a certain tolerance. So if your overlap is, less than 0.05 of a millimeter, then tolerant imprinting can help get around that issue that normal imprinting might struggle with. The other suggestion I have for anyone wanting to do something like this is to use the Coreform Cubit GUI first to get the hang of things, to figure out how you want to group your components together, to help troubleshoot. It's much easier to troubleshoot visually bad imprints because you can see which curves have imprinted and which haven't. But once you've used the GUI to get hang of things, use the Python or C++ APIs. It will help you monumentally. You can, version control your scripts. That's invaluable. Helps you keep track of your grouping. Stops you having to click on every little piece that you want. It is a massive time saver. And also, another thing I just wanted to note is don't be afraid to go back and change your CAD. If you've got a problem with a large overlap and you can't imprint it, go back to basics, go back to what you made and change it so it works. You might have just drawn something up slightly wrong. You might have made it a millimeter wider than it should be. So go back, make sure your geometry that you're starting with is sound. And with a little bit about imprinting and merging said, I just want to do a quick demo to kind of show how I might start doing something like this. So here's one I made earlier. This is a smaller version of the master geometry, which I prepared. So if we look at list totals, we can see that there are only 133 volumes in this model, but that's more than enough for an example. So what might we want to group together for imprinting and merging? Let's get rid of the top of the baked bean can, which is this tokamak, and let's see what kind of structurally we need to be stuck together. So a great start is this main vacuum vessel body, and these supports that go around the vacuum vessel body radially, and they help support these radial arms, which in turn support many other components. But let's just focus on these for now. If I wanted to select all of these, I'd right click and select similar volumes, which is a really useful feature in Cubit and will save you loads of time in large CAD assemblies that have a lot of symmetry or similar components. So now I've got all of those selected. I can select my vacuum vessel and I can draw it. And let's just have a look at this. So I would like these pieces to be imprinted and merged together so that when I mesh them, the resulting mesh is continuous. Nothing will fall into oblivion. Everything is nice and sound. So let's get one of those small bites prepared. To create one of those to get a small bite prepared, I'm going to create a group and I'm just going to call it vacuum vessel for ease. To vacuum vessel, I'm going to add this, the main vacuum vessel body, as well as these internal supports. So I select similar volumes, and then I go vacuum vessel, add vol in selection. In selection's really valuable in Qubit. It allows you to use what you've chosen in the graphical interface in the command line and makes life a lot easier. So now I've added all those volumes to this group. I can try and imprint the volumes in this group. Let's try and do this first with normal imprinting. So let's go imprint vol in vacuum vessel. You can also use the group ID if you don't want to type each time. So I could have gone imprint vol in group 34, but I'm going to name it by name for freeze. So that's imprinted, but has it done it properly? Let's start having a look. If you select something in the Qubit GUI, you can press I to remove it or to hide it. And now you can start to see the issues. None of the curves of the back surface of this support have been imprinted into this vacuum vessel. Let's try and look at some of the others. Oh, that's really strange. For this one, part of it has been imprinted, but halfway down we've lost track. So this hasn't gone quite as weird like. How would we undo that? What we can do is we can say regularize the volumes that we just imprinted. So the vol in vacuum vessel. This way, we remove that overlap. Everything's nice. Let me just move my zoom bar out of the way. Oh, sorry. I would like to know why that imprint didn't work. I'd like some kind of idea. And for that, I'm going to use one of the power tools within Qubit that can help you visualize any potential overlaps in your geometry. So to get power tools open, I just went to view and then I added power tools. And then down here on the right, and then in here, you can start playing around with volumes. So I would like to, oh no, sorry, I'm on the wrong tab. Here we go, volume IDs. I want to see if there's any overlaps going on between these components. Let's turn all the rest of it off and let's look at volume overlaps. So say, what's this component? This is 3212 and this is 618. Let's draw vol in vacuum vessel. Let's get this one again because this one, oh no, I removed the imprint, my bad. Let's have a look at some of these. Let's select two of these and see if there's any overlaps we can have a look at. And Qubit finds one volume overlap. And if we right click and we draw that volume overlap, we can see that there is a teeny tiny slivery overlap between the vacuum vessel and that support, which made standard imprinting or caused standard imprinting some troubles. So let's draw vol in vacuum vessel again. And this time, let's try tolerant imprinting. To do that, I just say imprint tolerant, vol in vacuum vessel. And if you're wondering what the tolerance value that Qubit will use to imprint is, well, you can change it manually yourself by saying tolerance and then typing in a value. But I'm just going to use the default for now, which I think is 0.05 of a millimeter. So let's try tolerant imprinting, see how that goes. This will take a second. It inherently takes a little bit longer than standard imprinting because, well, it's got to, search within some bounding regions. But if it works, it will be worth the wait. Fortunately, I've done this many times before this webinar, and I know it won't take too long, but it will take a second. 64%. The tension is building. Hey, and we're done. Okay, let's have a look at these again. Hey, that's what we want to see. That's some nice clean curves imprinted onto this curved surface on the inside of the vacuum vessel, and they all look brilliant and nice. Now that this like topology, these like surfaces have been implemented, we can merge the volumes that are in vacuum vessel together. So I'd go merge vol in vacuum vessel, and we get some nice output that tells us we've consolidated 12 pairs of surfaces. There are 12 pairs or 12 sets of these supports, so that sounds about right. So that kind of just goes to show how in these really large CAD assemblies, tolerant imprinting, you kind of have to use it, because unless your CAD is absolutely perfect, you're going to run into just a few troubles. Even if every alignment in your CAD assembly is great, you're going to run into a couple of odd ends. And then once you've imprinted and merged everything nicely, then you can actually start to mesh. And this is what I made earlier again, just to show off that when you do imprint and merge properly, you will be able to mesh these large geometries with little hassle. You might have to tweak some mesh sizing for individual components, but all in all, it's a lot easier having properly imprinted and merged everything. Okay, let's have a chat about useful commands when you're working with lots of geometry. When you're working with thousands of parts, you'll spend most of your time selecting things. You won't be doing a lot all the time, but you will want to select a subset of your geometry. So that's where these commands come from. They help accelerate geometry selection. So like I showed in the example, you can create groups, give them a name, and then add volume, surfaces, nodes, vertices, whatever you'd like to your group. And that will help you deal with having many parts a lot easier. You can select similar volumes, like I showed, which saves a lot of time when you have a lot of symmetry or a lot of similar parts going on. And you can also use selection qualifiers. So, for example, you can use except. Say I want to select every volume in group 5 except the ones that are in block 2, because actually block 2's got parts that are composed of a different material, and I didn't want to select the bits that are made of copper or the bits that are made of graphite. I only wanted the volumes in group 5 which were made of steel, so I excluded the ones in block 2. You can use in, so for example, select surf in volume 4 to get all of the surfaces that compose volume 4. And with is really useful for getting a subset of a group. So if I wanted all the non-imprinted and merged surfaces in a volume in group 4, then I could select the surfaces in the volumes that are in group 4 and then say with is merged equals false. That is merged equals false says, these are not imprinted and merged. I want the ones that are maybe exposed to the air, so that they're not going to be hidden by adjacent components. You can overcome small overlaps in CAD assemblies using tolerant imprinting, like I mentioned. And then if you find an imprint didn't work very well, then you can quickly revert back to your unimprinted geometry by regularizing. You have to go back to your regular old CAD. Once you have done the tough bit of imprinting merging and you've meshed, you probably want to evaluate your mesh. When you've got thousands of parts, they're going to be of different length scales, and you're probably going to need to tweak your mesh sizing for these different components. And Cubit's mesh metrics can help give you some insight as to where you should tweak that mesh sizing. So if you use Cubit's mesh metrics to output quality of all your tetrahedra, you might be able to see that, hey, this component actually has really poor quality tetrahedra. I should give it a smaller meshing size. And that can really help inform you when you're dealing with many, many parts, because you don't want to go through and do that manually. Yeah, you can use Cubit's mesh smoothing functionality as well to help alleviate some poor quality elements without having to remesh or change your mesh sizing. Mesh smoothing kind of can move nodes around to alleviate some really, really poor, say, sliver tetrahedra. And that can be really helpful, because if you're meshing a large geometry, meshing can actually take a long time, and actually smoothing instead of remeshing might save you that time. So to prove that all of this stuff actually worked, I'm going to show some of the simulation results that used the tokamak model. Now, the first simulation results I'm going to talk about are gravity, because gravity is a great litmus test for imprinting and merging. If parts are massively displaced, for example, on the right, this central column component is falling through the floor of a fusion reactor, which we would not like to see happen in real life, then it probably indicates that you missed an imprint or a merge. And thanks to Luca, by the way, for all of the figures that you're going to see in this section. So yeah, gravity is a great first one to run to test if you imprinted and merged properly. If you did, you might get results that look a bit more like this, which are a lot prettier than things falling through the floor. The results here are actually, they're on the right order of magnitude when compared to the real tokamak. They're probably a bit less than you'd see on the real thing, but it's actually hard to get measurements of the displacement of the real device because it's smothered in concrete to avoid any neutrons escaping, essentially. So yeah, it's a bit difficult to get proper measurements to compare to, but we are on the right order of magnitude. Oh yeah, I'm sorry, there's the displacement magnitude as well. Then let's look at some pressure differential simulations. So this was analyzing the impact of operating conditions on the tokamak. The vacuum vessel, as the name suggests, has vacuum conditions on the inside. So there's going to be a pressure differential between the atmospheric pressure and the vacuum conditions on the inside of the tokamak. This particular simulation made a lot of use of the select similar feature within Qubit to produce the boundary conditions on which you can enforce either atmospheric pressure or vacuum conditions. You have to choose every surface that's on the outside of the tokamak and on the inside of the tokamak. And selecting them one by one would be a massive pain to produce these large side sets. So actually selecting a subset of them and then choosing every similar surface means you can create that side set a lot quicker. And it was really helpful here. The displacement results in the picture are magnified by, I want to say, a factor of 100, I think. So don't worry, atmospheric pressure is not bending steel at will. It is just to show off that there actually is some displacement. And then we've got a bit of a mesh stress test. So we did some frequency domain simulations to see if we could see what the resonant frequencies were of different components within the structure. So what we did here is we took the bottom surfaces of two of the legs and we applied some oscillatory motion in the x-axis of varying frequency. And this resulted in various components within tokamak becoming resonant, which you can see on the graph in the bottom left. And really in this context, this is a great mesh stress test to see that everything, again, is imprinted and merged properly. The first couple of times we did this, there was the odd panel flying off once you start shaking things. Parts were going everywhere. And actually, that meant that we needed to go back into Qubit and maybe tweak our tolerances for our imprints and make sure everything's sounding okay. Yeah, a couple of useful resources to chat about that didn't really fit into elsewhere in the presentation, but I really wanted to mention because they helped me a lot. So the Qubit, C++, and Python API is really good. It is brilliant because it means you can use Qubit on non-graphical HPC systems, which means you can access high memory nodes, which you might need when you're generating a massive mesh. Like I mentioned earlier, using scripting allows you access to version control and repeatability. It reduces your chances of human error. For example, you didn't click the right volume in the GUI that you meant to click. Actually, if you just use a volume ID in the API, you'll never make that mistake. It's really good. I recommend that you kind of try it out when you can. Qubit's overlap detection, which I also showed in the example, is great for locating problem points. You might have in your CAD software, you might not have a CAD software that you use to prepare the model which you import into Qubit. You might not have suitable overlap detection methodology, or it might not be as rigorous. And actually using qubits can really help locate problems that are otherwise difficult to find. There's also the Exodus HDF5 output in Qubit. Using a large Exodus format, I could not generate this mesh. It's too big. You need HDF5 files to handle these large meshes. And also they read a lot quicker into Moose. Initially, some of the previous to using HDF5 with a smaller version of this mesh, loading in the mesh alone took way too long. It took a large chunk of our simulation time just to read in the mesh. The other thing I'd really recommend you have a look at is the documentation on the Coreform Cubit website, because actually having some explanation as to how the features in Qubit work, being able to get a feel for them, how do they function, will really, it'll help give you an intuition for how to use them. And yeah, I found the clarity on there to be really invaluable. So I was very appreciative that that documentation actually existed, because sometimes for other pieces of software it doesn't. And so, yeah, thank you for coming to listen. I hope that someone might find this helpful. I went into making this thinking, what would I have wanted to see when I started this project? I've got a couple of links here. One is to the archive of the first paper we've submitted, which relates to all of the results I showed you. It goes into preparing the model and the various simulations we did. And also, I've put my UKAEA email down in case anyone has any extra questions that they'd like to send over. I will try and get back to you promptly. But yeah, thank you very much for coming along. And any questions, I'm happy to take now.
Bill, excellent work. That was a very interesting project as well. Thanks for all the time you put into preparation for the webinar. A couple of questions. First of all, so you mentioned that you learn things in the GUI and then you move into just using the command line, and that's mostly what you were demonstrating was being in the command line. So the question is, how long did you use the GUI before you just decided to use the command line, and that would be faster?
I used the GUI until the amount of volumes that I had to wield around was difficult to use graphically. When I started getting into the kind of thousands or hundreds mark, I realized I needed to use some of the geometry selection tools to effectively and efficiently get through preparing a lot of this. And so that was kind of when I learned that I could do, in group except in block, and when I could do draw surfaces with is merged if I wanted to see which surfaces had been correctly imprinted and merged. Yeah, when it got to a reasonable number of surfaces and volumes that I needed to handle, that kind of prompted me to say I
Hmm.
want to get good at using the GUI now and actually learning all of the keywords.
Okay, great. Thank you. From Patrick, great talk. Thanks, Bill. Is the C++ you created available openly? Really curious about the use cases there.
Yeah, so I need to double check if I can share the actual script that I used to generate the geometry or the full geometry. Um, So I don't know the answer right now. But what I definitely could share is sort of a framework for doing what I did. So I would share I know I can share the kind of C++ for loading in a mesh, making sure qubits all loaded properly, for meshing and imprinting and merging. I could share sort of a framework for it. I would hopefully be able to share the actual thing, but I need to check because the paper isn't fully published yet, and yeah, need to check a couple of things first.
Okay, great. Another question, did you use Qubit for any hex meshing or was it all pet meshing for this project?
So for this project, it was all tetrahedral meshing, just because it's such a large assembly. I decided to go with a meshing scheme which kind of allowed me to get something out quicker. I think that I would have been able to get a hex mesh together if I had kind of maybe spent the time. But to me, I'm quite interested in seeing if we could do an IGA solve with this. So I feel like I might as well go straight to IGA instead of spending the time mapping the correct components for hex meshing. So currently it's just tetrahedra, but I have a mind on other methodology in the future.
Yeah, no, I agree. Maybe we could do a follow-up webinar showing this in IGA. That would be
I'll be
great.
back. I'll be back.
Let's see, just a question. If the presentation slides can be shared, is that, would you be comfortable with that, Bill, or do you need to?
Most of them I'm 100% sure can be. I need to potentially the results slides with some of the images from the
Yeah.
paper. I would need to remove or put Black Sharpie over. But yeah, otherwise, I'd definitely like everyone to have, the useful commands and everything like that.
Great.
And Matt,
Okay, yeah.
will we be uploading this to YouTube afterwards as well?
Uh-huh. Yep. Yep. Yeah, so we'll work with Bill and then we'll send out a link to both the recording and we can link to the shareable slides as well. Um okay, yeah, we'll just wait if there's any other questions for another minute or two, but um let's see. Okay, you've got another one that's come in. What is the final size of the full mesh in like gigabytes?
Oh, that's a great question. Um, so I can tell you in element count, it came to about 130 million tetrahedra. I can't off the top of my head remember gigabyte count because um, I get mixed up between the first order and second order meshes. I want to say it was about 10 gig, but I would have to double check before I go on record
Okay.
as saying that.
Yeah,
But it was good few gigabytes on the order of good few.
great. Question from Kyle. Did you have any issues with negative Jacobians in Moose due to the few poor quality elements that you had, assuming a thermal
Yes.
mechanical model?
Yes, I did indeed. Especially so, um, I tried to move over to doing a second order tetrahedral solve within Moose, which I was able to generate the second order tetrahedral mesh within Qubit just fine. But within Moose, obviously the second order solves are slightly less inherently stable, and I needed to go back and really tweak my element quality and element sizings settings to prevent negative Jacobians because I just had way too coarse or too thin, too spindly elements in certain places. I also was able to alleviate some of this by changing my Moose preconditioning settings. Certain preconditioners um, resulted in me getting negative Jacobian errors a lot faster than others. So yeah, part of it was tweaking my element sizing to make sure that everything was of decent quality. Part of it was actually going into the CAD again and removing certain curves that I'd forgot to delete and the meshing software is trying to comply to. And part of it was messing with my Moose settings to get an adequate preconditioner in there. But I have felt the pain of negative Jacobians at certain points.
Did we ask what was the calendar time from when you started this project to when you had all the simulation results that you needed?
So it was to getting from the very start, from this model to actual results is about a year. So that's doing the CAD for the missing components, that's imprinting and merging, that's meshing, and then actually, well, I didn't actually do the simulation runs. Luca did those, but getting those outputs, it was about a year, but it's not completely linear. Kind of it starts in Qubit and you make a simple mesh and then you run simulations on that. And then actually you need to add more components in the CAD. And it's all
Mm,
quite a cyclical process that took about a year. Yeah.
mhm. Okay. A question from Ollie. How long does it take to generate a finite element model from importing CAD to writing the input file? So
So
I'm assuming that means, yeah, and maybe Greg, maybe you can provide some color on how you're interpreting that. I wonder if it's just from when the CAD's imported until you are.
Yeah, I think just for each of those cycles, I mean, are we talking, is this representative of 10 hours of work? Um, is it 40 hours of work, 1 hour? I think that's kind of if you could spitball
yeah.
or rough estimate.
So in terms of like the actual compute time, in terms of like once I've got it all scripted and ready to go, I think meshing the entire model to just run imprinting and merging and then meshing procedures takes hour and a half, 2 hours to get it all ready to go. In terms of the human hours of imprinting and merging and like getting to the point where I had those scripts ready, that was a couple of months, because mostly because different groups require different tolerances for your tolerant imprinting and merging. So a lot of the time, the default tolerance is absolutely fine. But every now and then you'll run into a group of components where actually you need a slightly higher or a slightly lower tolerance to successfully imprint and merge. And that's quite a manual procedure. So that was me on the GUI looking at curves, seeing if they're correctly imprinted and merged. That's on the order of a couple of months, I would say. But actually running the scripts, a couple of hours.
No, that's fascinating data. Question from Li Ping. Were all of these results solved by Moose, or were there other simulation tools that you used?
All of the ones in the paper are solved by Moose, and we have experimented with running a version of this model using MFEM as well, to kind of, just test it in other frameworks. But yeah, all of our results are from Moose at the moment, really.
And Bill, did you use the provided modules from Moose, or did you have to write your own physics module?
I could use the provided solid mechanics modules, which was brilliant. After when the mesh was ready, I didn't have to do any physics kernel preparation. That was all good to go.
Great.
It was
Question. Oh, go ahead.
oh, sorry. I was just gonna, for clarity, it was linearized strains in Moose. It was, yeah, just small strain assumptions, linear elastic material properties, and all of that. So fairly simple kernel-wise solve.
Great. So Mark's asking if you ever considered using symmetry to accelerate both the meshing and the solve.
So I think we'd had some discussions about that, because obviously it is quite a symmetrical geometry, even if not completely. So, for example, these portholes, they're around the reactor. They're not completely symmetrical. So there are limitations geometrically as to where we can apply symmetry. But I absolutely understand that if you ignored those, you could do this a lot quicker by just doing a slice of the reactor. But part of the kind of drive of this project was to see if we could do a full scale reactor. We kind of, even though symmetry might absolutely have a place here in future, this is kind of, yeah, we wanted to do the whole thing to see if we could a little bit.
Great. See, another question. Have you used this model also for radiation transport, like with OpenMC?
That is on the way. It's not currently done yet, but that's where we're looking towards in the future. So there will be hopefully another paper kind of going into neutron transport, and potentially other physics after that. And kind of, now the model's made, we want to use it for as much, or at least I'd like it to be used as much as possible
Great.
for various physics.
Yeah, because it should be ready to go for that, right?
Yeah. Using the DagMC export and Cubit, it's pretty much good to go.
Yeah, great. Well, Bill, thanks again. It's been a pleasure to interact with you. And again, thanks for the excellent preparation and presentation. And thanks everyone for attending.